This session is all going to be about considering latent heat as for requirements of the IB physics course. To start off with, I want you to think back to an experiment you've undoubtedly done before. You were probably asked by your science teacher to heat up ice and record the temperatures over time. The graph that you saw probably looked a little bit like this, at least the initial stages anyway. Initially, the ice was frozen and its temperature was below zero, and it would increase at a constant rate. Then, as the ice began to melt, we found this change in temperature stopped. It stayed at the same temperature, that of 0 degrees centigrade, for a little while until all the ice had melted, and then the temperature continued to increase. It's probably where your experiment stopped. If you'd kept on going up though, you would have found out that at boiling point, so the point when the change of state between liquid and gas was taking place, again there'd be a moment when the temperature stopped increasing until all of the water had managed to turn into gas, and then the temperature will keep on increasing. Now, those two key stages where the temperature wasn't changing are what is described as latent heat. Now, latent heat is the energy absorbed during a phase change. So what happens here is that the temperature doesn't increase. Instead, all the energy is going towards breaking the bonds. So just moving them further apart. And that increase in potential energy is known as latent heat. And we're going to consider that a little bit more mathematically in this session. So, two types of latent heat. Specific latent heat of fusion. This is the energy required to change 1 kilogram of solid of liquid to liquid at a constant temperature. So that is the melting energy. Specific latent heat of vaporization. This is the energy required to turn 1 kilogram of liquid to 1 kilogram of gas. So this is the boiling energy, the amount of energy required to rip apart those particles and change from a liquid to a vapor. What you'll find is the formula that you'll use for this is you'll recognize the specific latent heat is normally given the letter L, capital L. Doesn't matter if it's for vaporization or melting, either way it's perfectly acceptable. This tells us how much energy is required to change the state of 1 kilogram of stuff. In your IB textbook, you'll find this as change in Q equals, which is the amount of energy going in, required to change a certain mass multiplied by the specific latent heat. So that's the formula you'll be given in your formula book. Now, you would not be required to remember any specific latent heats of fusion or vaporization, but there's a whole range. It very much depends on the chemical structure of the material that we're talking about. As we can see, often we'll find that there's a quite dramatic difference between the value for fusion and the value for vaporization, because the huge increase in potential energy which is required as a change from a liquid into a gas. Any questions which talk about latent heat of fusion or vaporization normally have to consider a real life situation. So things don't exist at boiling point and melting point. What you have to do is you have to heat them up. So when dealing with questions about this, you've got to think about where heat is being given out, where heat is being absorbed, and try not to miss any parts. So sometimes heat's going to be given out, sometimes it's absorbed. I'm trying to take you through a question which considers all of the elements. It's quite a complicated question, but it takes you through all the aspects that I need you to be aware of. So here's my example question. Calculate the total energy that must be transferred to a 0.5 kilogram block of ice at minus 12 degrees if it is to be completely converted into 0.5 kilograms of steam at 108 degrees. This question doesn't just ask about change of state. In fact, it asks for two change of states, but also considers some heating up processes as well. In fact, there's 5 sections which you've got to really think about. So let's take through those 5 sections. The first section the energy required to raise the temperature from 12 degrees to 0 degrees. Here we're just considering the specific heat capacity of ice. So here we've got 0.5, which is the mass, times 2,100 times 12, and that gives us a value for the amount of energy required just to heat up the ice from minus 12 to 0 degrees. The next stage is the amount of energy required to melt the ice. So this is a state change, so we've got to think about the latent heat here. In this case, the latent heat of fusion. So the mass multiplied by the latent heat of fusion gives us another value for how much energy is required. Next stage, we need to heat up the water and raise it from 0 to 100 degrees. So again, we use the specific heat capacity of water. When we reach 100 degrees, we reach another state change. So here we need to think about the energy required to change water into steam. And again, we're considering about latent heat here, but now we're talking about latent heat of vaporization. So the amount of energy is going to be equal to the mass of the water multiplied by the latent heat of vaporization. And final step, the amount of energy required to heat steam from 100 degrees to 108 degrees. Again, we're going to need a different specific heat capacity of water, but this time specifically in the steam state. Last but not least, you need to think about the energy required for all of these stages is the sum of the total energies. So if we add those up, we find out how much energy is required to increase the temperature of ice at minus 12 degrees to steam to 108 degrees. My next question kind of indicates that this is not a one-way question. How much energy must be removed from 0.5 kilograms of steam at 108 degrees to completely convert it into a block of ice at minus 12 degrees? Well, the trick to this question is it's the same question as before. So if you know the answer, your solution is going to be exactly the same, 1.5 megajoules. The same amount of energy required to heat up a system is the amount of energy required to take out of a system, assuming that system hasn't lost any energy to any other places. Another question which we can consider, a block of ice of mass 100 grams and temperature minus 15 degrees was placed into a copper calorimeter, mass 150 grams, containing 500 grams of water at 25 degrees centigrade. Calculate the temperature of the final mixture. So here we've got to think about the energy going in and the energy going out. Okay. So energy from the water and energy from the calorimeter. These are the energies which have been used to melt the ice. So the energy needed to raise the temperature of the ice from minus 15 degrees to 0 degrees centigrade. That's one feature. We also need to find about the amount of energy required to melt the ice at 0 degrees centigrade. And then finally, the energy needed to raise the temperature of the ice from 0 degrees centigrade to the final temperature. So we're looking for 3 different steps. There's quite a lot of things going on there. Think about it carefully though. First of all, we're looking at about the change in temperature of the water, and we're also looking at the change in temperature of the calorimeter. This is the energy which has been used or taken to melt the ice. All that energy, in theory, has gone into melting the ice and changing the temperature of water and the calorimeter. So if we look carefully, you can follow through and you can find out that the final temperature is going to be 6.91 degrees centigrade. Look through that carefully. There's lots of interesting steps in that. Another example question. Here we're considering some students who decided to try and cool the whole of the school swimming pool down by 10 degrees. And they need to think about how much ice was going to be needed to solve this problem. Again, this is a problem of multiple parts. This time, a few things have to be estimated as well. We're assuming the length of the pool is 25 metres with a width of 8 metres and a depth of 1.5 metres. So sensible estimates there. That gives me a volume about 300 metres cubed. The mass of the water we're going to be assuming has pure water, so that gives me a value of 300,000 kilograms. Initial temperature is going to be about 25 degrees centigrade of the water, and I want to cool it down by 10 degrees centigrade. So the change in temperature of the water is going to be 10. I need to work out how much ice I need to put in there. So the amount of ice I put in there is going to be mass 1, and that's going to be the only unknown I have in this calculation. So I put all the values that I know in, and it's going to find out that I'm going to need 32,061 kilograms of ice to cool down that pool by 10 degrees, which is a huge amount. So, final recap. The formula you're going to find in the IB textbook indicates the amount of energy required to convert a certain mass of substance from one state to another.